Good morning, guys. Today is day 8 of Unit 13. So we are talking trig. And what we are doing today is called Pythagorean identities. We are going to just focus in on one specific identity. Technically, there's 3. You'll talk about the other 2 next year in pre-calc, but we're going to focus on just one. So the notes on the website are a worksheet. I changed the worksheet, I think, last year. And so when I printed it out, I didn't have it in the packet. Sorry about that. But we can just take our own notes for today. It's pretty simple. So as a little reminder, we're going to do example 1. Just to remind you where Pythagorean theorem comes in handy. So I'm going to shorthand what is given in example 1 on the notes packet. It says if the terminal side of an angle in standard position goes through the point -3, 2, what is the numerical value of cosecant of theta? All right, here's the important stuff. So the terminal side of an angle goes through the point -3, 2. Find cosecant of theta. I love these questions because they're just giving you the information in a little bit of a different presentation. So what I want you to do, draw yourself a set of axes. And then we've got the point -3, 2 that the terminal side goes through. So think, all right, here's -3, up 2. That's the point that the angle has to rotate and go through. So any angle in standard position would start here on the x-axis and then would rotate open so that it goes through that point. That's the angle that we're talking about. The cool thing is, because you know that exact point, what I want you to do is draw your triangle from that point down to the x-axis. And what that gives us is the actual dimensions of the triangle, because that means you went to the left 3, so that's -3. You went up 2, and then to get the hypotenuse, we can just use Pythagorean theorem. So you can immediately see kind of where this is coming in, right? So if we do a little Pythag, we'd have 2 squared plus, I can write it as -3 squared or just 3 because it's going to come out the same either way. And then equals, x squared. So let's see, 4 and 9, we get 13. Take the square root. That hypotenuse we're going to have as radical 13 here. Right. And then we can calculate the cosecant. Or actually, we can calculate any trig function we would need to. But cosecant, that is the ho of the ho-ha al. So the hypotenuse, radical 13, over the opposite 2. And bam, you're done. All right. So since these questions that we're going to be working on require Pythagorean theorem, there's actually something called a Pythagorean identity that gives us another way to be able to solve. But it's actually a really cool concept that we're going to see. So I'm going to slide this up a smidge. What I want you to consider is give yourself, again, a set of axes. And then I want you to give yourself the unit circle, which is code for the radius is 1. All right. On the unit circle where the radius is equal to 1, if we draw an angle, let's say over here, in the first quadrant, where it hits, we're going to call that point just an XY point. So when we drop down the perpendicular, we went over a distance of X, we went up a distance of Y, the radius itself is just 1 right there. All right. Using this triangle, if we use the Pythagorean theorem, which we know is just a squared plus b squared equals c squared, I want to fill in the values that we have here. Right? Now, the legs are always the a and the b. Technically, you can interchange them, but I kind of like this to read in a specific order. So I'm going to label this as the a, down here is the b. Hypotenuse always has to be the c. So in place of a, I'm going to plug in the y squared. In place of the b, I'm going to plug in the x squared. In place of the c, I'm going to plug in 1. All right. You could stop here, but where the identity really comes from is you have to think about which function is being represented by x and y. If you remember from earlier in the unit, y is equivalent to sine. So this is the same as the sine of the angle. And I'm going to put a little theta right there, sine of the angle squared. X is the same as cosine, so that's the same as the cosine of the angle squared. And then 1 squared just turns into 1. The one thing that you'll want to note, to lose the parentheses, you actually have to move where the square is. So the square comes inside and it's written as sine squared theta, but it means the same as whatever the sine is, you square it. And then here, this is cosine squared theta, and then equals 1. This right here is called a Pythagorean identity. And what that means is no matter what value of theta you plug in, it's always going to be true. All right? So as an example, to kind of show like how that works, I'm going to pick a pretty angle. So I'm going to slide up so I have a little more space here. And the pretty angle that I'm going to pick is, let's let theta just be like 30 degrees because it makes it a nice special right triangle, makes life easy. Right? So if I use 30 degrees, we can label our triangle. This would be 1. This is radical 3. This is 2. You guys are pros at that stuff by now. All right, so let's actually show how this works. So if we do sine squared of 30 plus cosine squared of 30, we want to show that it equals 1. And you can write this part down, or maybe just even just watch for a moment. So what I want you to remember is what we just said a second ago. That is the same as whatever the sine of 30 is. So you're going to take that value and square it. Whatever the cosine of 30 is, take that value and square it and show that it equals 1. All right, sine of 30, opposite over hypotenuse. That would be 1 over 2 squared. Cosine of 30, adjacent over hypotenuse. That would be radical 3 over 2 squared. All right, if I square the 1 and square the 2, that becomes 1/4. Square radical 3, that just becomes 3. Square the 2, that becomes 4. And then 1/4 plus 3/4 is 4/4 or 1. Ta-da, it worked. And that's the cool thing. It'll work no matter what angle you plug in there. I just picked 30 to make it pretty. So the reason that we look at this is this actually gives us a different way to be able to solve for that first question that we did, or any question that we do, by either using the method that we draw the triangle, or you could plug right into the Pythagorean identity. And I'm going to show you an example where you see that it's actually a little simpler to use the Pythagorean identity in certain cases. So I'm going to flip on over here. And let's do an example both ways so you can kind of see how they compare. So the example I'm going to give you, it says, if it is known that the cotangent of the angle, and it might use alpha in the notes, I'm just going to stick with theta, is less than 0, and sine of theta equals radical 7 over 3. Actually, I have a little white out here, so I can fix my little goofs. Radical 7 over 3. Determine the value of cosine of theta. And now the one little part that I might have hopped over in the notes there, where this is going to be the easiest is if you're given sine and looking for cosine. The Pythagorean identity works because those are the two functions that are listed together. Or if you're given cosine, it's easy to find sine. So here's a perfect example of that. We know the value of sine. We're going to be looking for cosine. Ding, ding, ding. This is when we want to use it. Okay. So if we use the Pythagorean identity approach versus if we draw the triangle, so we're going to do both. So maybe split your paper up here. All right, here's where the new part comes in. Write it down. The identity is sine squared theta plus cosine squared theta equals 1. Cool. Let's plug in what we know. This is what sine of theta is equivalent to. So we're going to plug that in right here and square it. So we have radical 7 over 3 squared plus cosine squared equals 1. Well, what do I want you to do next? I want you to actually square the number. So when you square, oops, there we go. When you square radical 7, it is just 7. Square 3, that's going to be 9. And then subtract 7/9 over. So when you subtract it over, don't overthink this. 1 is the same as 9/9 minus 7/9. You're going to be left with 2/9. All right. To get cosine by itself, you got to get rid of the squared, which means we take the square root and then square root of each part. So break this up. This essentially becomes radical 2 over radical 9, which is the same as radical 2 over 3. The one other catch to this is you have to remember that when we physically go in and take the square root, you have to consider that it's either plus or minus. So there is one little additional thing that you have to come up with here. Which one is it? All right. So here's where that one extra piece of information back at the start, you're told that cotangent is negative. That's so you can figure out what quadrant this thing is in. And then I'll know whether it's positive or negative. So this goes back to our notes from yesterday. So here's a quick ASTC, or if you remember, all students try cheating. I love you guys. It's just a way to remember it. All right. So this stands for where they're all positive. Sine is positive, tangent's positive, cosine's positive. We are told that sine is positive radical 7 over 3. That immediately gets rid of those two quadrants. All right. But when you are told back at the start that cotangent, which is the same as saying tangent, is negative, that means it can't be in quadrant 1. So that rules out quadrant 1. This thing is in quadrant 2. All right. Well, what do you know about quadrant 2? Well, in quadrant 2, cosine is negative. So this thing is going to be negative. And that is your final answer. So cosine of theta is equal to negative radical 2 over 3. So you plug in, you solve for the value. The last consideration is you have to figure out where is it so that you know whether it's positive or negative. All right. How would we have done that same question by just drawing a triangle? Well, drawing the triangle, sorry guys, I'm a little crooked on you. There we go. We would have probably started by doing the whole ASTC. So obviously I'm not going to make you redo it, but we would, we'd figure out where we're supposed to be and we'd figure out that we're in quadrant 2. And then that's where we would draw the triangle. So over in quadrant 2, we would say, hey, if sine is equal to radical 7 over 3, that's the opposite and the hypotenuse. So the opposite side is the radical 7, the hypotenuse is the 3, and then we would use Pythagorean theorem to solve for this side right here. So we would do a little x squared plus radical 7 squared equals 3 squared. And you can very quickly see how this is going to end up as radical 2. When you go to put the radical 2 here, you would have to remember, hey, it's going to the left. That means it's a negative value. So no matter which way you go about it, the Pythagorean identity or drawing the triangle, you have to make sure that you bring in the negative at some point, whether based on where it's drawn or in the end based on what quadrant it's in. All right, so there's my negative. And then I would say, all right, cosine of that angle is a over h. And so now it's negative radical 2 over 3. And there's that same answer. Okay, we're only going to do one more example, but this one really showcases, I think, a situation where it's kind of nice to use the Pythagorean identity over the triangle. Because I would say that first example we just did right here kind of shows that, like, all right, both ways are fine. So you could always default to the last one, right? For the third example here, I'm going to give you that cosine of theta is equal to 0.198, and that theta falls between 3 pi over 2 and 2 pi. And then what you want to do is you want to find sine of theta to the nearest thousandth. All right. If you need to pause to be able to write things down, just pause the video. Otherwise, I'm going to keep moving. So in this case, there's a couple things going on here. I am given sine and cosine. I'm looking for sine. That is a perfect time to use the Pythagorean identity because I'm given one piece. I'm looking for the other part of it. So here's the rule. Sine squared plus cosine squared equals 1. This little detail, this is telling me what quadrant the angle's in. So this is telling me that if the angle's between 3 pi over 2 and 2 pi, it's somewhere over here in quadrant 4. All right, so hold on to that little tidbit in a moment. All right, let's plug in. We don't know sine, but we do know cosine. So 0.198, we're going to square that guy and then go on our way. So grab your calculator, unless you can do that with mental math, and then bravo. Otherwise, 0.198 squared. All right, it's a long decimal. You can write down all the numbers. You're tough. All right. From here, get sine squared alone. So you're going to subtract from 1. So 1 minus, go grab that number right there. That leaves us with 0.960796. And then take the square root. So this is a lot of calculator work. So square root of that guy right there. All right, it's going to give you a big old long decimal, which is why in the directions we said round that answer to the nearest thousandth. So I'm going to write down 0.9802 blah, 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 which two things, nearest thousandth, 3 decimal places. So 980 will get it done. Last thing, think about the sign. So when you do the sign, come back over here. In quadrant 4, A, S, T, C. Quadrant 4 is where cosine is positive. We were solving for sine, which means in quadrant 4, sine is negative. Right? On your homework, do you have to write that statement? No, but that's what you need to be thinking. So put a negative in front of that. So what I should have done actually is when I took the square root, gone plus or minus to remind myself, and then if it helps, circle that minus so you don't forget about it. Okay. So in lieu of a set of like written directions, the idea is you can use this when you are given sine and ask for cosine or vice versa, plug in, solve the equation, determine the sign. Those are your steps. All right, guys, good luck with the homework. Reach out if you have questions.